So what we're going to do is that we are going to extend our basic repeated measures ANOVA into a multivariate repeated measure. So we have the measurements over time, and then we're going to have multiple dependent variables. There's many names to repeated measures in MANOVA. There's some people also call it doubly multivariate MANOVA, profile analysis, and we're going to cover profile analysis, but there's a separate kind of profile analysis that's called latent growth or latent profile analysis. And I really think the only difference there is just the emphasis on latent variables. And it has its own separate kind of test because they are latent variables. But it's very similar. I feel like if you understand profile analysis, learning the structural equation modeling type of profile analysis is not that difficult. Let's just recall what the repeated measurements entails. So for example, we would have 3 different time points, and we are measuring a variable. In this example, I have blood pressure. And then you are going to measure people on their blood pressure, but you're going to do it at 3 time points. Maybe you have interventions between them. Maybe you got them to exercise, diet, or I don't know, whatever new treatment there's available. So you expect that over time there's going to be a change, or maybe you don't expect it and you want to see it to that it's stable over time. But the important factor here is that these people need to be measured at the same time. So when you would have them in a spreadsheet, you need to have a way to identify them, to know that this person here is the same person here and it's the same person here. I've seen so many projects crash because people didn't keep track of this. So don't let that be you. I kind of already talked about the purpose. So the assumptions are very similar to what the assumptions that we had for your generic repeated measures ANOVA. So for MANOVA, they're going to be pretty much the same. We're going to check for independence, and I've mentioned this before. So independence, you can check on just the design, whether the participants seem independent. But your textbook actually suggests to check by what's called the interclass correlation coefficient. I think if you're in a situation where it's a classroom, an apartment, a hospital, a company that's being tested, and you have really good reason why you don't think they're that independent, it's definitely worth checking. It might lead you to, might force you to have to do a different type of analysis though. Then we would check our homogeneity of variance, covariance matrices, and our multivariate normality, which we check with Shapiro-Wilk. But then we have the special assumption that's only for repeated measures, the univariate or multivariate level. And sphericity, we have to check whether it's a univariate design or a multivariate design. It's also known as circularity. It doesn't actually have to do anything to do with circles or spheres, believe it or not. So I'm created a sample data set to kind of explain you what sphericity is. So let's say I have a data set and I have people on it, and they were split in control and 3 different treatments, which I just label A, B, C, and D. There's 5 in each treatment. I mean, this would never fly in the real world. We would need more. But I'm just going to try to show you what sphericity entails. So the hypothesis for sphericity is that the variance of the differences, emphasis on differences, as the key word here, between A and B, so between control and treatment, and then A and C, control and treatment 2, and control and treatment. So all of those differences, and then when I do the difference between treatment 1 and treatment 2, treatment 1 and treatment 3, all of those differences, the variances that I calculate from all of those differences are going to be equal. And the alternative always disagrees, so to speak. The alternative says that at least one of those differences is not equal to the rest of them. So I went ahead and graphed the pairs of differences. So on the x-axis, I have the difference between A and B, A and C, and so on. And you can see there's quite a few that are different, A and B and C. And then I also went ahead and graphed the standard deviation of the differences. And you can see there's definitely something going on between B and D. And actually every combination with treatment 3, you can see that the standard deviation is wider. And remember what the null hypothesis is telling you is that for sphericity, these variances are equal. And we can see that they're not equal, at least graphically. We would still have to perform like an actual hypothesis test to see if they're statistically different. But ideally, what sphericity wants is that there's not a significant difference between this. If there was a statistically significant difference and you have the violation of sphericity, first, you don't make the assumption. Second, it's very likely that your F statistic, the one you're going to get from your MANOVA, is biased. And once it's biased, like it puts the whole study into question. What can cause for you to violate that assumption? In the old days, when I learned this procedure, they would tell us that to have it spaced out, especially if they were treatments, you want them to have a respectable amount of time between the treatments. I'm not sure if there has been any newer research about what's the best recommendation. So if you need to do this type of analysis, I would definitely encourage you to look a little bit more into it before you actually run the experiment. Ideally, you would be able to randomize the treatments so that when you do these differences, it's not an artifact of where they were positioned, like where those combinations are happening. Just pay attention to that. So one of the advantages from using repeated measures designs is that the subjects act as their own control. So this hypothetically would translate on having smaller sample sizes. I think there's a caveat to that. I think for example, I learned statistics in an agricultural school. So if I checked on my lettuce every 3 months, it was always going to be there. But with human subjects, we have the issue of ethics. So if they decide to drop out of the study at some point, we cannot force them to participate. So that's missing data. So my recommendation, we would disagree with what your textbook says. I do think you need a larger sample size with repeated measures. The longer this design, the larger the sample you should start with. Okay, so let's move on into profile analysis. So it's just a modification on MANOVA. And again, we're going to focus on the differences between, I don't want to say treatment, between the groups or factors that we're interested in. And so it's very similar to hoteling in that way, and we're going to have to do that type of data manipulation. A big part of doing profile analysis is just to creating plots to see how the subjects behave over time, how their differences behave over time, or if there's no differences, or if there are no differences, excuse me. So what is the purpose of profile analysis? It's used by researchers to identify whether you have a group, 2 or more groups that show a distinct profile in a test, basically. It helps see the pattern for the groups. Ideally, I believe you would want all groups, especially if you're doing like academic testing, you probably want all the groups to have the same trajectory. If there's a group that doesn't have that trajectory, that's where, again, that's important to know, and it's probably something that can be useful for policy and allocating resources. So profile analysis is the multivariate equivalent to repeated measures or a mixed ANOVA. It's mostly concerned with test scores. So whatever field where they have to do a test, what they do is that they're going to rank the participants, and they rank them by finding the differences. And then we plot the trajectory and we see how the different groups are doing in that particular test. You can do it with inventories, for example, the big five. So put a little side note on this. I really believe that for latent variables, there's a better approach, which is latent growth. The thing is, you have to learn structural equation modeling first to get into latent growth. But I feel like the procedure is very similar. It's just you have to do check for different assumptions for structural equation modeling and latent variables. But they're similar. It's become a new trend to just use latent growth for latent variables. It's in the name. Whereas profile analysis, you would use it for non-latent variables. So for example, for tests for like GRE, SATs, they're going to have subscales. So you can rank order those subscales, and then plot the trajectory, and then actually do some statistics to see if they're significantly different in whatever groups that you're looking at. And you can do it for the subscales as well, for an inventory. Profile analysis is used in two major ways. The first one is the one that you kind of already picture, where you have a dependent variable, and then that dependent variable is measured over time. That's sort of what we understand for the most part for repeated measures. The second way is when you have several dependent variables and they're not necessarily being tested on the same thing, but there's two or more measurements on that dependent variable. But those measurements could be like reading, writing, calculating. But it's the same unit, but what's being measured is different over time. That said, it's very important that the measurements are on the same scale. And remember, because we have to rank them by creating those subtractions similar to what we did in hotellings. And once you're doing that subtraction, it's going to be very weird if one variable is in one scale and the other is in a different one. And just, you don't even have to think about the statistics of it. Just think about whether you're trying to plot it and they're not on the same scale. It would just look awkward and probably misleading. So it's very important that they're all on the same scale. What kind of research questions can you answer with profile analysis? So the main question that you can answer is whether the groups have different profiles, whether they're following the same trajectory or not. Ideally, you want them to have parallel profiles. That's what I would want if I was looking at groups of students that I'm teaching. I want them to all learn the same way and at the same time. Another research question is, you might suspect that there's a group that has a higher profile or a lower profile. I think both would be interesting. And that's what we call flatness. We're looking at the flatness of the slope, basically. And I'll show you in a couple of graphs in a minute so you know what I'm talking about. So profile analysis is asking three basic questions. Are the groups at equal levels across time points or observations? In observations, you can substitute the word there on the repeated measures. Do the profiles exhibit flatness across time points or the repeated measurements that you have? Are the groups parallel between time points or observations? And I'm going to go back to this questions when I show you the graphs. But basically, if you say no to any of this, you're rejecting the null hypothesis. And it really depends on what you want. You're rejecting the null hypothesis, and it means that the test is significant. Whether that's good or not, it's going to depend on the research question. So equal levels. So equal levels is asking, are the groups at equal levels across time points or across the repeated measurements? This is the simplest form of profile analysis that you could potentially do. The test is just asking, does one group score higher on average across all measures or time points? And to evaluate it, really, you have to find what the grand means for the groups are. Here I just made up some data, and this is what it would look like. They kind of have that same trajectory, and really what we want is, are there differences in the means? That's what we want to see. And this is not very sophisticated. Like, you would just compare the means in the univariate with an ANOVA, with a t-test, etc., etc. Question you can answer with profile analysis is flatness. Do the profiles exhibit flatness across time points or across the repeated measurements? So what we do here is we compare the multiple segments between the time points or repeated measurements to see if there was a change. How would we know? Well, remember what a slope of 0 would look like. It's just a flat line. Except for us, we have time points, and this is actually for equal levels, but we do have the time points, and what we want to see is that this is not a flat line and that it's not 0. Ideally, if you are testing maybe children in math and you keep testing them every year, you probably want to see growth. So you don't want to see a flat line when you're testing for that. So the null hypothesis is that the segments are 0. If you reject that, then you can go ahead and actually test the groups individually to see if there's change in the segments for the groups. And the way you would do that would be, just depending on the groups, you could do hotellings or you could do math. The third question you can answer with profile analysis, parallelism. Are the groups parallel between the time points or observations? And the way you answer this is, well, we already know how to use it. It's MANOVA. And I'm pretty sure you know what parallel means. We want to see if they kind of have the same trajectory, that there's no interaction between them. So here it's a good example when you do have parallel profiles. Even though one group is doing better than the other, obviously, they are having that same trajectory. You can also have the situation where people tend to think of the interaction when there's like a real cross between the groups, but here they're no longer parallel. Once we get to the third time point, their profiles are no longer parallel. I don't know what happens here. That's, you would need to know the literature to know what's happening. But I can tell you just by looking at the graph that the groups no longer have a parallel profile here. So let's actually do a data example for profile analysis. I'm going to use a data set from Tabashnik and Fidel, my favorite textbook. The only issue with it is that all of the examples are in SAS and SPSS. We're going to use a hypothetical data set, meaning it's not real data. It was just made up for this example, and I like it because it's simple and it's a small data set, so it's easier for us to follow what's happening in it. That said, we still have to do a lot of data management to be able to run assumptions, to be actually able to do the MANOVA. So even though it's small and simple and it was created small and simple, we still have to do a lot of data management. And this is not R specific. You would have to do this in SAS or in SPSS or whatever software you would be using. It's very rare with repeated measures that you would just have a file that works perfectly for everything that you want to do. It actually is not just repeated measures for any kind of data, but I do notice that when it's repeated measures, for me, it's when it requires the most data management. So it's a data set that represents 3 different occupational groups: belly dancers, Y; politicians, Y; and administrators. Weird. And they were asked to rate their 4 leisure activities on a scale of 1 to 10. So read, dance, TV, and skiing. So we don't have a situation where they're being really measured over time. It's the same unit that it's responding to 4 different measurements. So that's a little tweak that we're doing here for profile analysis. The research question is going to be, do the groups have parallel profiles? So the file that we're going to use is the multdb, and I think it's in a text file. Before I get into the data management of it, I just wanted to show you what the data looks like. It looks pretty clean. It has ID, names, so belly dancers, politician, and administrators, and then the 4 measurements for the leisure activities. I went ahead and also ran summary, and I can see that I don't have any missing data here. There's 5 of each group. Everything looks cool. So to be able to create the graphs that I showed you earlier to check for equal levels, remember I have to look for the grand mean. So I need to do a little bit of data manipulation here. For the belly dancers, remember it's just rows 1 to 5. Let me go up a little bit. So 1 to 5, those are the belly dancers. And I want to calculate the mean for reading, the mean for dancing, for the mean for TV, and the mean for skiing. So that's what we're going to do here. I'm going to store everything into belly MN for mean, and I just did calculate the mean for belly $ reading, sorry, and then the same thing for dance, TV, and skiing. So this is going to store 4 means, 4 grand means, and this is what they are. I did the same thing for politicians. Before I go into that, I just tell it I just want to look at rows 6 to 10, which are 6 to 10 politician, and then I'm going to calculate the mean for each one of this mini columns that I created, and then I get store everything in politic MN. I do the same for administrators, and I went ahead and create a nice table for you to look at. It's not very aligned, but it's what I can do in R right now. So I put the grand means there. So what we're going to do next is just we want to manipulate the data a little bit so that we're going to create a new data set with this grand means so that we can actually get those plots that I showed you earlier. So, and again, you would have to do this no matter what software you're using. I used to love using select cases in SPSS. I don't know, I'm weird like that. So if you had to do it in SPSS, you would still have to compute the grand means for each one of those mini columns, mini data sets, and then select cases to create the new data set and export it, create a new file, and then do the actual graphs. So all of this work wouldn't change. So let me just guide you through this lines of code. So I'm going to create a variable called group. I am creating a matrix, and I'm going to have belly, politic, and admin, and I want to repeat it 4 times. So belly, 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 and then politic, 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 and so on. So it's repeating it in this same order. So the order in which you type in it here matters. Then I want to create another column called variable, and that is going to have the leisure activities. So again, I'm going to create a matrix. I'm going to repeat the values, and then I'm going to tell it what I wanted repeated. So in this case, I want reading, dancing, TV, and sky, and I want to repeat it 3 times. Read, read, read. And then 3 times again for dance, 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 and then the same for TV, and then the same for sky. Okay, so that's creating this column. Now I want another column called average. So again, I'm creating a matrix, and then I'm gonna bind the columns. And where did I get these numbers? I got them from the same table that I just created over here. So let me actually highlight this in a color. So here I went ahead and highlighted everything so that you could see the pattern. So it's the variable average. I created a matrix, and I want to combine the columns. So the order in which you enter it does matter, because if you don't enter them in this order, you're going to get different results, period. And it's going to be incorrect. So here I highlighted where I'm getting. So it would be 6.6. So that's the belly dancers reading. That's why it needs to be there. So the next thing I need is politicians reading. So I go politicians and reading. That's at 5. The next thing I need is administrators reading, which is also a 5. So it would be this 5. Oops, it should be pink. You know what I mean. And then you repeat that until it's created. Then I went ahead and created a data frame. I just joined those columns and I call that a new file. All of this work is just so that we can plot it. We are going to plot it using ggplot2, which hopefully by the time we get to the dirty data lecture, we're going to learn a little bit more about it. But for now, we're just going to use our basic structure for plotting. We need to call the library ggplot2. The function is called ggplot. You give it your data set, and this is called aesthetics. Essentially, you have to tell it the x and the y, and then the grouping variable. So the x is going to be the variable. The y is going to be the average. And then here we just tell it which one is the group, which is the types of occupations. This is, you can just leave it as is. We want a line chart that's telling R that we want lines. And then all of this plus signs, I personally find them confusing, but you can essentially add features to it. I wanted a line chart, that's why I used geom_line, but you could have plus geom scatter, and that would make it a scatter plot and so on. Again, this is the next lecture. And then the labs is just to add the labels to it. So in the X, I want dependent variables. And then on the Y, I want mean of leisure. And actually, I should have said grand mean there. And then geom point is just to add that little point in our data set. I store everything into a variable called line, and then I call for that variable. Because if I store it in there and I never call for it, it's just going to be somewhere in R hidden, and I'm not going to be able to see it. So this is what my graph data would look like. Remember, I have mean leisure here. I have my dependent variables here. So before, when I was showing you what broad profile analysis was, I had time here. In this case, I just have the 4 measurements: dance, read, sky, TV. And here I just plotted the means that we calculated by doing all that data manipulation. So just by looking at this graph, remember the research question is, do the groups have parallel profiles? No, they don't. Just look at this mess. So I can already answer that question. Maybe not with statistical significance, but I can already answer it just by looking at this. So now we're going to do the differences between each of the measurements. And we're going to do that so that we can actually create a new data set where we're going to run the ANOVA on. So that's more data management that we have to do. I don't think it's that difficult, at least. So I created a new variable called RD because it's essentially just a subtraction of the vectors read minus dance, and then DT, dance minus TV, and then TV minus skiing. So each one of these are going to be a vector, and you can see what's inside of them. I'm calling them here, and that's what makes them print over here. So cool. Those are the differences between the measurements. So what we're going to do now is create a new data set, and that data set is going to contain the differences. So I created this variable called occupation, basically, but simplified. So I'm saying repeat and bind the rows by belly, politic, and admin. And I want it repeated 5 times for belly, and then 5 times for politic, and then 5 times for admin. And that's what it's doing here. It's creating this column. And then I'm gonna save everything into a data frame called diff for differences. So I just put occupied there, and then I just put the vectors I already created that have the differences in there, and that's what it would look like. It's not bigger than what we already have, but it is different than our original data set because what we have here is differences. So now that I've created those differences, I'm going to check for the outliers within the differences. And the way we do it is the way we always do it. Here's our degrees of freedom. I'm going to use for the columns just from 2 to 4 because the first one is categorical data, so I don't really need to check for outliers there. I just want to check on this 3. So I do the same thing. I do my cutoff. I use my Holanova's distance. This is my cutoff score. It says true. Remember, if it said false, that meant there was an outlier there. So I don't have any outliers here. I still run the code to store everything in no out, and that's mostly out of habit. Like, the code was there, so it's just easier for me to keep going with the name conventions that I already used. So no outliers were removed using my Holanova's distance. I'm going to move on into checking my assumptions. So I'm going to check sphericity. And to check sphericity, I'm actually going to have to use the original data set. And I'm going to put a big asterisk on this. So we don't necessarily have to check sphericity for profile analysis. Well, we don't necessarily have to check sphericity for this particular example because they're not times. There's just multiple measurements on the same person. But I am going to show you how to do it just in case you one day have an example of profile analysis where you do have, instead of multiple measurements, you have the times. And the reason I wanted to show you is because it takes more data management that you have to do to be able to do it. So this is what our data set more or less looks like. It actually looks more like names, read, dance, TV. I added the time 1, time 2, time 3, just to give you an idea of what it would look like if they were time measurements. I know the colors look pretty ugly, but I don't know what I was thinking at the moment. So this is what's known as a wide format. Why is it wide? Just because the measurements are each in its own column. I am pretty sure SPSS will always have this type of format in their data sets, and they also... I am pretty sure for SPSS, for the most part, it will demand a wide format to be able to do repeated measurements. That's why it's very popular. But it also has another function to do what we're going to do. And if you ever need it, I can help you with that. I'm going to show you how to do it now in R. But what I want to be able to test a sphericity is I want what's called a long format. And look what the long format looks like. It has all the valley observations, and then it has the actual rating, and then it would have the time, time 1, time 2, time 3, time 4. And for us, it's not going to be essentially the time, but this would be, let me see, purple, it would be reading, and then it would be the 5 measurements for dance, and then TV, and so on. So that's what we're going to do. We're going to manipulate our data so it looks like the long format. And the way we're going to do it is we're going to use the package Tidyverse, which is super popular. Everyone loves it. I think it's okay. I'm going to use the gather function. So when I actually started using R when R was barely known, and it wasn't because I wanted to. A professor made me. And there used to be something called reshape function. That stopped working. And then when I started my PhD, there was another function called melt and cast that would kind of do the same thing. Like when you would melt it, it will turn into a wide format. And when you use the cast function, it would turn it into long. A few years ago, when I created this notes, it became the gather function. But when I was going over this lecture again, I just noticed there's a new one. It's called pivot long and pivot wide or whatever. So just be aware, this changes periodically. Like people are constantly creating new functions to do this more efficiently. I actually think gather is pretty good compared to what melt and reshape were. But it is a very popular function. Like it's a very popular thing to do in data management. That's why there's always a new function to do it. Anyway, we're gonna do it with gather. Cross our fingers that it works and it doesn't get discontinued. So I call for the package called tidyverse. I'm gonna store everything in long.data. So I have gather, that's the function. I put my data set here, the one that I want to transform from Y to long. Key is gonna be, let me show you. It's gonna where I want to have basically the time variable, which is the read, ski, the other one, TV and dance. So for us, it's not time because that's not our example data set. So I just call it names. But if you had times, you could call it time. And then the value, this is to create a new column that's going to have the scores. So for us, the score is just the rating. And it just puts 7, 8, 5 in there. That's what it's doing. And then here, you just tell it from where to where are the measurements. Let me pause. So we have 4 columns. Or if we had time data, it would be from 4 times, time 1, 2, and 3. So you're just telling R from this column to this column. Those are the repeated measurements that we're going to be using. So that's what this little piece is doing. And I actually have another example of this in the dirty data lecture, which as I keep recording this, I just feel like I should have put it before this lecture. So that worked. It didn't give me errors. So I'm just going to inspect what long.data looks like. So here's ID. That's just the number in the data set. The names would be what we, if we were using time data, repeated measurements in time would be. So all of this are going to be read 1 to 15. And then 1 to 15 dance, and then 1 to 15 TV. This is our long format. And then for each one of those, we have the actual rating for that activity, leisure activity. Cool. Now that I have it in a in a long format, I can check for sphericity. And I am going to check sphericity by using the Mauchly, I don't know, Mauchly test for sphericity. The test of sphericity, that's what I'm going to use. Remember, the null hypothesis for this is that sphericity is met, that the variances are equal, and the alternative is that sphericity is not met, that the variances are not equal. So ideally, your test of sphericity is non-significant, and you retain the null hypothesis, meaning that sphericity is met. But if you find your significant test for Mauchly test of sphericity, meaning less than 0.05, I had a typo there, then it means you have to do a correction. So there's 2 types of corrections. It's the Greenhouse-Geiger or the Heinfeld corrections. So the Greenhouse-Geiger is actually more conservative than the Heinfeld. They're trying to do the same thing. They're trying to estimate the epsilon. The closer that epsilon is to 1, that means sphericity is perfect and everything's just perfect for your study. That's never going to happen, at least not with real data. You could simulate your data and it would be perfect, but for the most part, it's never going to be that big. The lower it gets, that means that the violation of sphericity is greater and greater. So if you want to be conservative, it's recommended that you look at the Greenhouse-Geiger one. If you have a situation when it's less than 0.75, it's also recommended that you use the greenhouse. If this greenhouse is 0.75 and then you look at the Heinfeld and that's above 0.75, then it's better to just report this one. Either one, my experience is this one is always close to 0.75, and then I end up reporting this one anyway. I do think there's a benefit of reporting this one if you want to be very conservative about your results. So there's many. There's way too many ways to calculate the test of sphericity in R. But I found the easiest one is the EC ANOVA, and I think we're a little bit familiar with it already. So I went ahead and just used that one. So I imported the library EC, and I'm going to store everything into this variable called SPH for Spear. So I wanted to look at the long data that I created specifically for this test. Here in the dependent variable, I'm going to have the score. Whatever continuous number was measured, that's what I'm going to put in there. Here, you're always going to put whatever distinguishes the subjects. In this case, it's going to be the ID. And here's going to be the within subject. So that's going to be the time. For us, is TV, dance. For us, those are going to be read, dance, ski, and dancing, I believe. Those 4 measurements. I believe this is type 3. So even though it's called EC ANOVA, I actually find the output super hard to look at in my experience. So here we have, so here in the box, you can see the test of sphericity, the W, and my p-value is not significant. So this is good. That means I'm meeting the assumption of sphericity, and I actually don't have to do anything else. I can just report I did Moxley test of sphericity, and it was not violated. You report a W and you report the p-value. Remember to only use 2 decimals here and then 3 for the p-value. Don't give me that whole chorizo there. I don't want to see it. So let's say you have a significant test of sphericity, then you would have to look at the Greenhow geyser, and this is close to 75. That's dangerous. Because it's that close to 75 and not lower, I'm going to go to the Heinfeld, which is this it just says HFE. This would be the W for that. I'm sorry, the epsilon for that. These 2 yellow ones are the epsilon, and then these 2 pink ones are the p-value. Here, because it's not lower than 75, and it is just by, a thread, a hair, I would report the Heinfeld, and then I would report the p-value. And here's my example of how I would do that. Let's move on to normality. Like MANOVA, essentially we're doing a MANOVA, but we're just transforming our data into differences, and we're going to do the MANOVA on that. But like MANOVA, profile analysis is robust to violations of normality. The only situation where it won't be is when you have a smaller number, your sample size is smaller than however many dependent variables you have, or you just have unequal ends in your groups in your dependent variable. So then you're going to have a situation where you might violate normality, and it's going to be really bad. If you are unlucky enough to have small and unequal sample sizes, then what you can do is look at the distributions to see how normal they look. And if possible, you might be able to do a transformation on the dependent variables before you run the MANOVA. So I'm going to check my normality assumption now. I'm going to set up for the assumption. So I always do this fake regression. I'm going to use just I'm back using the diff dataset and just the columns 2 to 4 that has the differences in there. I run my fake regression, I put everything into fake, then I get the standardized residuals, and I get the fitted residuals. This command is just telling R to graph me a really nice histogram for the standardized residuals. I wouldn't say it looks normal, but it's definitely not terrible. And you also have to remember our sample size is very small, so we have to lower our expectations. I went ahead and, I ran my Shapiro-Wilk test. the way I always run it, I use this package. I transpose everything. Well, I only transpose the columns with the continuous data. I ran Shapiro-Wilk on that, and I do not reject the null hypothesis. That means that I um, meet the assumptions. So looking at the histogram, it looked okay-ish, but more importantly, it did pass a formal Shapiro-Wilk test. Cool. I'm going to check linearity now. So whenever we're looking for parallel profiles, we need to have linearity between the dependent variables. So Tabashnik and Fidel actually really recommends looking at the scatter plots for linearity. I think this is like the weakest type of checking for linearity, but that's a recommendation. So I went ahead and just used GG pairs on our continuous data. And I don't think it looks great. This is a high correlation between these two. I'm definitely worried about this one because that correlation is very weak. You look at the scatter plot and it's pretty random. The thing is, even though it looks really random, I couldn't say that this is a curvilinear relationship. It doesn't look like it anyway. So I could say it passed the linearity assumption. Or I didn't see anything that gave me a red flag that it was not linear. That's what I would say. So then I went ahead and checked homogeneity of variance, covariance using the heaplots package. Here I put the columns that I'm interested in, the numeric ones, and then I put what tells the column that has the groups, which was the very first column. And yeah, the very first column. I hesitated for a second. So I got all my information, and I do not reject the null hypothesis, and that's actually good. It indicates that I met the assumption. Cool. Next, I'm going to go ahead and do a power analysis. So there's no specific function for profile analysis and G-power, of course, but everything here is going to be in MANOVA essentially, so we can use the MANOVA repeated measures within between interaction. We're going to use our alpha 0.05, our power 0.80, the number of groups or levels on the conditions, that's going to be the number of predictors is going to be the number of independent variables, and the number of response variables is going to be the number of dependent variables essentially. We're going to use a large effect size. It's 0.40, so that it doesn't ask for a really large data set. So here's what it would look like. It's the F-test family, MANOVA repeated measures. A priori, our effect size was 0.40, alpha 0.05, power is 0.80. The number of groups is 3: belly dancers, administrators, and politicians. The number of measurements is 4. And here's this number of measurements, but remember, this can also be, if you were looking at time measurements, so it would be the same, the 4. And it recommends 46 people. We actually have like 15, so we're not doing that great. Our study is definitely underpowered. Dun, dun, dun. So we just write that. We recommend to keep collecting data. And then we're finally going to do our data analysis. And it's going to be a lot easier than everything we've done already. I'm going to column bind my dependent variables. So all of the differences, the columns that have the differences in them, and I'm going to save them in a variable called outcome. I'm just going to tell R that occupation is a categorical variable and it's a factor variable. And remember, its occupation is belly dancers, administrators, and politicians, so it's definitely what I'm trying to make it so. And then I'm going to run MANOVA. I put my dependent variable here, and then I put the independent variable over here. And I tell it from which data set. It's going to be the difference data set. And I'm going to store everything into model. So I'm pretty sure I mentioned this in a previous lecture. Here I have to bind the dependent variables because doing it one by one is not going to work. It's going to give you three different tables. And it's if I actually write it like this with commas in here, it's just going to drive R crazy for once because it's always R driving us crazy. That's why I have to bind them before I put them into the model. Cool. So the next thing I do is just use the summary function. This is where I store, oops, this is where I store everything that was calculated from this MANOVA function. And I'm just asking for here for Wilks lambda. And there's a reason why I highlighted that. I'll show you in a minute. It was significant. So that's telling me that there's a difference between the three occupations. And we have evidence that there are no parallel profiles for the three occupations, which we already know just by looking at the graph. But now we have a p-value, so we can feel accomplished about that. That was a joke. And then I do the same for Pillai, and then for Hotellings, and then for Roy's greatest root. And you can see all of them are significant. So that's good. We don't really have to think too much about this. We could just report Wilks lambda if we wanted to. Or we could do like a nice table and report all four. There's really no consensus on how to report that. Actually, I'm lying. The consensus is if they're all significant, if they're all pointing to the same conclusion, the consensus is to just report Wilks lambda. The next thing I did was to calculate the effect size. So for profile analysis, we're not going to be able to just pull Pillai out of R or the output that we already created. We actually have to follow this formula. 1 minus the square root of Wilks lambda. And I just put lambda there, but I'm referring to Wilks lambda. You can also use the heaplots package. So I'm going to store everything in ES. I'm going to round it to 2 digits just to make my output cleaner. I'm going to calculate eta square. I tell it where I store my analysis for MANOVA. Here I don't want to do an ANOVA. I want the partial eta square, and I want it from Wilks. And then it gives me 0.72. You don't want to write all this stuff. Oh, sorry. And then this part is I'm rounding it to 2 decimals. That's what that's saying. Notice that parentheses closes over here. So you don't want to do all of that. You can just do 1 minus the square root of Wilks lambda. And that's the purple one that I highlighted here. And that is exactly the same thing. And then you can just round it yourself. How do I report this? So I perform a profile analysis on 50 participants. We did screen the data for multivariate outliers. We didn't have any missing data, so we didn't have to do anything there. I kind of report the repeated measurements, which are the read, dance, TV, and skiing, the type of groups, which is going to be my dependent variable. I mentioned that I did it in R, and I mentioned the version. Then I go on into reporting the MANOVA, and using the Wilks criterion, I just report the F for the MANOVA, the p-value, and the effect size. Cool. And then I just said, I remember the effect size tells you how much variance is being explained. So in this case, is 72% of the variance is being accounted by the profiles of the 3 groups. Nice. Figure 11, and I just call it 11 because I have a lot of figures, kind of shows that the profiles are not parallel. And the significance that we found in that F value in the Wilks criteria also tells us there was a significant difference between the 3 occupations. And we can see that belly dancers have the highest profile. Administrators were in the middle, and politicians were at the bottom, of course. Actually, there's no of course here, it's made up data. And you don't just have to talk about the graph, you can also show the means that we already calculated. in earlier in this lesson, so you can just have a table or you can write it in text. It's up to you. I'm really into tables this semester, so I'm trying to do everything in a table. So I show that. Table 1 shows that the belly dancers rated the leisure activities higher than administrators or politicians, and administrators were kind of in the middle. And you could go ahead and actually do an ANOVA with this data if you wanted to keep reporting p-values and post hocs, etc., etc.